Hello everyone, my name is Ikshu Nathwith, and this is the first in a series of 2 talks on a new 3-manifold invariant called SL2C Floer Homology. In today's talk, we will define the invariant and go over some of the algebraic geometry used in its construction. In the next talk, we will discuss a related not invariant. First, I'd like to go over some of the motivation for defining this invariant. The basic idea is that we would like a version of instanton Floer homology, except using the gauge group SL2C instead of SU2. But this introduces several problems. The first of which is that the moduli space of flat SL2 connections on a 3-manifold Y is potentially very singular. Of course, we can resolve this problem simply by perturbing the defining equations for this space and then attempting to achieve transversality so as to make a smooth moduli space. This is the standard approach that one would use in gauge theory. And if you do so, then there are the so-called instanton corrections in the Floer differential that involve counting solutions to a certain PDE. However, in the case of SU2, one has very powerful theorems such as the Uhlenbeck compactness theorem that allows one to compactify the moduli spaces of instantons and do some analysis on them, such as perform the necessary counts. Unfortunately, for a non-compact gauge group, you lose these tools, and the analysis in counting the instantons becomes quite difficult. But there is one good thing about SL2C, which is that it's a complex gauge group. And for a complex gauge group, the physicists predict that there are actually no instanton corrections contributing to the differential. That is to say, provided, of course, that we do not perturb the equations. So that's what we're going to do. We are going to, this third point here means that it might be possible to define SL2C Floer homology completely algebraically without talking about PDE at all. So essentially we're going to leverage this third good point here, ignore the second bad point. We will not perturb the equations. If we did that, then there would be instantons, and we're going to have to deal with this first bad point in that case. We're going to have to deal with the high level of singularities that are present in the character varieties, and to do that will require a bit of algebraic geometry. The first ingredient of our story will be the moduli spaces that we're interested in, which are the character schemes of groups. These are often referred to as character varieties, even in the situations when they're really not varieties. You can associate one to any finitely generated group gamma, although we'll be mainly interested in the case when gamma is the fundamental group of some manifold. To any group, you can think of its set of representations into the group SL2C as an affine scheme in the following way. If you just had the free group on G generators, let's say, then the representation scheme, the set of representations, is just a product of G copies of SL2. And then for an arbitrary group with some relations, those relations define R of gamma as a subscheme of SL2 to the G, an affine subscheme. We'll also be interested in the character scheme, which is the quotient of the representation scheme by the conjugation action of SL2. Here we've taken the GIT quotient. But actually we'll mainly be interested in the irreducible representations. So here chi-ir refers to the locus of characters, of course, coming from irreducible representations. And it turns out that the irreducible representations are the stable locus for this GIT action. So restricting to irreducibles, you can think of this GIT action as an honest quotient by a free action of SL2. Now let's focus on the character schemes of the manifolds that are of interest to us. So let's let Y be a closed orientable 3-manifold. That's what Y will always be in these talks. And we have some Heegard splitting of Y into 2 handled bodies, U0 and U1, glued together over the Heegard surface sigma. So that exhibits Y as a gluing diagram, which yields the following push-out diagram of groups by the Van Kampen theorem. And applying the representation functor, representations into SL2 being a contravariant functor, flips all of the arrows, and then taking the quotient with respect to the conjugation of action of SL2, an action that respects all the maps in this diagram, we obtain the following picture in terms of character schemes. And in fact, the character schemes here have a lot more structure than just being schemes. It turns out that the character scheme of irreducibles for a compact surface sigma is actually a holomorphic symplectic manifold, by which I mean a complex manifold with a complex valued symplectic form. So in particular, it is even complex dimensional. And the character varieties of the handle bodies then include into this holomorphic symplectic manifold as complex Lagrangians. So that means that the character variety of our three-manifold Y is thereby viewed as a Lagrangian intersection. So now what we're going to do is define an algebraic invariant associated to complex Lagrangian intersections, and we'll use that to define our three-manifold invariant. The algebraic invariant of complex Lagrangian intersections that we will be using applies the machinery of perverse sheaves, which are a very well studied tool in algebraic geometry, particularly useful for understanding the topology of schemes or singular algebraic varieties. So I'd like to offer at least a quick definition of what a perverse sheaf is. So perverse sheaves are a certain class of objects in the bounded derived category of constructible sheaves on X. That is, constructible sheaves of abelian groups, denoted d upper b lower c of x. And to define a perverse sheaf, we need to understand the notion of the stalk of a sheaf. So given the inclusion of some closed point, we can consider the pullback of the sheaf to that point, as represented by j lower x upper star, that is the pullback of the sheaf to the point little x. And then we can consider the set of all points with non-vanishing stalk cohomology. And that is the notion of the support of a sheaf. The support in degree I is just the closure of the set of all points with non-vanishing stalk cohomology in degree I. There is a dual notion called the co-support, which is the same idea, except instead of taking the stalk, we take what is called the co-stalk, j upper shriek. Unfortunately, it'll take a little bit too long to define the co-stalk in general, but it is the Verdier dual operation to the stalk. So in the case of x being a smooth point, the co-stalk is nothing more than some degree shifted version of the stalk. And this object, f, in the bounded derived category, is called the perverse sheaf if it satisfies a support condition as well as a co-support condition. Rather than trying to look at the definition too carefully, I'd like to just give you a picture of at least the support of a perverse sheaf. So this picture is from Jordy Williamson's Illustrated Guide to Perverse Sheaves, and this is supposed to represent some scheme of complex dimension D. And here we see that the cohomology in degree 0 is supported on at most zero-dimensional subschemes. And the cohomology in positive degrees simply has to be 0. The cohomology in degree, let's say, -1 could be supported on curves, in degree -2 on surfaces, so on and so forth, all the way down to in degree -d. The cohomology in that degree could be supported everywhere on the complex dimension D scheme. And below that, in degrees -t-1 and below, it must be 0. So this can be deduced from the definition I gave. Well, I'm really looking mainly at the first part of the definition, the support condition. The support condition tells you everything except the vanishing in degrees less than -d, but in fact, that can be deduced from the co-support condition. Okay. We'll actually be interested in a very special type of perverse sheaf called the perverse sheaf of vanishing cycles. It is a generalization of the concept of the Milnor fiber. So let's quickly review the Milnor fiber of a function on some smooth scheme U. complex valued function. Let's assume its value at x is 0. In such a situation, we can consider the Milnor fiber of the function f at the point x, defined as follows. So first you take a small ball around x, and then we consider the intersection of that ball with the fiber of some value delta, some small value delta, even smaller than the radius of the ball, under the function f. This we call f sub x, and it's called the Milnor fiber of f at x. The perverse sheaf of vanishing cycles, then, it's a perverse sheaf on the entire scheme U, and it has the following property, that if you compute the stock cohomology at some point x of this perverse sheaf, then it'll return the reduced cohomology of the Milnor fiber at that point. And one of the basic results about Milnor fibers is that they are contractible away from the critical locus of f. So this means, in particular, that the perverse sheaf is supported on the critical locus. It turns out one can associate a perverse sheaf of vanishing cycles to any complex Lagrangian intersection as follows. So let's start with some holomorphic symplectic manifold and two complex Lagrangians with big X their intersection. First, we can apply the Weinstein neighborhood theorem to find some nice charts. For any point in the intersection, we can find a small neighborhood inside the symplectic manifold, and an isomorphism, that is a holomorphic symplectomorphism, from that neighborhood to a neighborhood of that point inside the cotangent bundle to L0. And under this isomorphism, it'll take the piece of L0 inside of our neighborhood to the 0 section, and it'll take the piece of L1 in our neighborhood to, well, it'll take it to the graph of some one form inside the cotangent bundle to L0, and the Lagrangian condition means that this one form is in fact closed, and since we're in the local situation, it is then in fact exact for some function df. So in other words, the image of L1 is the graph of df. And in that case, the intersection of L1 and L0 is the critical locus of f. In this situation, we are going to try to build a perverse sheaf of vanishing cycles on the entire intersection x. To do this, we'll first need an assumption that L0 and L1 are equipped with what we call spin structures, by which I mean choices of square roots of the canonical bundles of those Lagrangians. Now, spin structures in this sense are parametrized by the first cohomology group with z mod 2 coefficients. So actually, if our Lagrangians were, say, simply connected, then they are unique. So in this situation, we have the theorem of Abouzaid, which says that there is in fact a perverse sheaf, which we'll call P L0L1, in the category of perverse sheaves on X, denoted perv of X. This is actually an abelian category. And it's characterized by the property that if you restrict the perverse sheaf to some open neighborhood U, like in the Weinstein neighborhood theorem, then on that neighborhood, it's actually isomorphic, essentially, to the pullback of the perverse sheaf of vanishing cycles associated to the function f. Remember, here f is the generating function for that Lagrangian L1. It turns out, yes, that one can do this construction locally on all these charts and then glue them all together to come up with this global perverse sheaf object, assuming we have these spin structures. Now, I should say that Abouzaid's work is based on the work of Dominic Joyce on derived critical loci, and Joyce shows that one can define a perverse sheaf on any d-critical locus. Abouzaid's theorem is an extension of that to the case of holomorphic symplectic manifolds. So a lot of this then rests in some sense on Joyce's work and derived algebraic geometry, but we won't really be using any derived algebraic geometry in this talk or in the construction of our invariant. We'll prefer to use just classical models instead, classical algebraic geometry. But in principle, you could consider using the full technology, say, of Pantev, Toin, Vahke, and Fetsotsi on shifted symplectic structures. By their work, there is a perverse sheaf on any -1 shifted symplectic scheme. Lagrangian intersections are a type of -1 shifted symplectic scheme. And the advantage of using that approach means that you could potentially work with singular symplectic manifolds. Well, not manifolds, but singular symplectic schemes. This could be good because then you could take into account the reducibles. Remember, we were always ignoring the reducibles, preferring to work with the irreducible representations. One reason was because that allowed us to have a holomorphic symplectic manifold. But potentially with derived algebraic geometry, that can be upgraded. That would be an interesting direction for future work. So now we have all of the ingredients necessary to define our invariant, which we'll call HP of y. So first, we use the Heegard splitting to view our character variety, the character variety of irreducible representations, as a complex Lagrangian intersection. And then associated to that complex Lagrangian intersection, we have this natural perverse sheaf as given by Boussi's construction. We'll call that P of y. Then the theorem proven by Abouzaid and Manolescu when they construct this invariant is that this perverse sheaf is actually an invariant of the three-manifold y. In other words, it does not depend upon the Heegard splitting. So we'll refer to its hypercohomology then as HP of y. That is, the hypercohomology of the character scheme valued in this perverse sheaf. That's what we'll call sheaf-theoretic SL2C, Floer homology. And I should mention that there's also a version that uses representation schemes and takes into account reducibles, giving an invariant called framed SL2C Floer homology, which we denote HP sharp of y. Of course, the representation schemes, as I said, are very singular in general. Even the representation scheme of a surface is some singular scheme. It's certainly not a symplectic in any sense. But there is a trick that one can use to view the representation scheme inside what's called a twisted character scheme of a surface of one greater genus. So this applies the notion of torus-summed Floer homology of Verheim and Woodward. But I won't get into that now. Alright, so that concludes the first talk and our construction of the invariant HP. In the next talk, I'll say a little bit about an associated not invariant. Thank you.